Welcome to our final session, final slide set relevant session, I would say. So, last week we discussed some very important things about operating systems. We discussed interprocess communication, or we finished the topic of interprocess communication. One of the main topics of operating systems, definitely. And for this week, I have the final slide set prepared, and it's about one of the one of the most recent or most modern topics of operating systems. It's about virtualization and in parts also emulation. So that's definitely one of the topics where we had most innovation in the last years, maybe in the last 2 decades, if we talk about operating systems. So this slide set is about, as I mentioned before, virtualization, and we will talk about benefits and drawbacks and limitations, definitely, because you cannot do everything with virtualization. You cannot cover all demands, or you cannot use virtualization for all scenarios in a useful way. We will talk about the difference between emulation and virtualization, because that's often mixed. It's mixed with each other, and we don't have one single virtualization technique around. We have many different sorts of virtualization, many different concepts, and these concepts have a strong influence in the architectures, and also again in the benefits and drawbacks of the different virtualization solutions around. So, and as always, we have a dedicated slide set about virtualization. The same here. It's we have a dedicated exercise sheet for this slide set, as always, and it's exercise sheet 10. So, what is virtualization, or what are the fundamentals of virtualization, the overall concept or overall motivation? The basic idea is or industry, whoever, we want virtualization to assist us in split the resources of computer systems into smaller portions, smaller parts, and assign these portions to applications or operating systems. And these multiple applications or entire operating system instances, we want them to run on one hardware. And one technical term which is really important here is the virtual machine technical term. A virtual machine, that's what we create usually by using virtualization solutions, and we demand it should behave as a real computer, as a real physical computer, and in effect it's usually an isolated environment on a physical machine. And depending on the virtualization concept implemented, we are talking about entire machines which are created in a virtual way, or just instances of one single operating system, or maybe just environments, isolated environments for single applications. But overall idea is it should behave like a physical machine, and we have an isolation of the application. So we try to have more stability and maybe also security. So yeah, one thing, the applications should not learn about being inside an isolated environment or inside a virtual machine. Um, this should be transparent. Otherwise, we would need to modify the applications, and that's something we don't want. The virtualization software needs to catch all the requests of the software we want to operate inside the isolated environment, needs to catch these requests and converts them in a way so that it works well inside the physical environment, inside the host operating system if we have one. So, as mentioned before, we have many different virtualization concepts, and in this slide set and in this session here, I want to give you an overview. So the aim is that at the end of this slide set you have a basic understanding of these different virtualization concepts, and you have a basic idea of for what scenarios are what virtualization concepts well suited and others not. One thing before, virtualization is not a fresh technology. It's not quite new. IBM, always IBM, maybe IBM again invented this many decades ago in the 60s and 70s. First products became available back in these times in the context of mainframes, big computer systems, and general idea back in these days was quite similar as today. People wanted to operate many instances for single users or for single applications, just to utilize the hardware, utilize the computer system in a more efficient way, and in a way that more people and more applications can be executed at the same time. So that's history, but now present day, yeah, we have different virtualization concepts, and so I prepared some information about each one of them. And so we just start at the very beginning, and yeah, maybe in 80 minutes or so we will finish this topic and finish this semester in regard of slide sets at all. So we start with partitioning. Partitioning is a very useful concept of virtualization. General idea is we have, as always, independent subsystems or instances, but not like virtual machines here created by a virtual machine capable software. No, it's the functionality is implemented by the firmware of the computer system. So you cannot deploy this feature afterwards. You need to buy a machine which already has partitioning implemented, and machines which have this feature implemented are usually quite expensive. Yeah, we are talking here about mainframe systems or mid-range systems, which means it's a little bit smaller than mainframes but not inexpensive. And the partitioning concept is quite popular when we talk about the power CPUs of IBM. That's not something we have in desktops or usually in server systems today, and it's also not quite, it was not common a decade ago, so it's basically a niche product. Yeah. Um, but it's a very strong concept, and the implementations are very strong. Um, on a mainframe or mid-range system which has partitioning implemented, you usually can create many hundreds or thousands of independent operating system instances at the same time. Usually we talk about Linux instances, and that's a very strong hardware we are talking about here. Um, for modern personal computers or server systems made of commodity hardware, partitioning cannot be implemented because the CPUs we have in our personal computers or server systems, they have just CPU virtualization implemented, and they cannot create entire systems in a virtual way. So for systems we use every day, it's not the right virtualization concept. But just to demonstrate you, it's a quite powerful concept, and solutions exist which are very powerful. Maybe the most popular example of a system that used partitioning is the Watson system by IBM. So the Watson system, around a decade ago, it was smart enough to win the Jeopardy challenge. That's a very popular television quiz in the United States, and yeah, usually humans play this against each other and can win some money. And yeah, a decade ago, the IBM Watson system was able to win against human beings. And this Watson system, it was a cluster of 90 IBM server systems with such a power CPU, and with such power CPUs, sorry, several CPUs and several cores. Also a big amount of main memory when we compare it to the perspective of a decade ago, but it's still a lot for today. 16 terabytes, it's not bad today. And these systems, it was 90 nodes, and each partition was able to run an IBM Unix or a Linux instance, and it's really independent operating system instances. So every physical node has one hypervisor. The hypervisor is the component which is used to create and control these partitions. Yeah, it implements the functionality. The technical term hypervisor you will see several times in this slide set. Yeah, and we have some interesting features implemented here, like live partition mobility, which means you can relocate single partitions from one physical machine to another one without interruption, or active memory sharing. So partitions can utilize the same main memory, and also transparent compression. So compression of main memory, and that's a very very rough when we talk about CPU utilization, but IBM said so depending on the application, the compression of the main memory is sometimes better than relocation or swap in, swap out operations. So partitioning, yeah, interesting concept, but not our way to go for our daily steps we need to do, daily things we need to do. The next concept I want to show you is hardware emulation. Hardware emulation is not really virtualization, but as mentioned before, it's often mixed. Yeah. So and many virtualization techniques also implement in parts emulation. So in virtualization, we specified we want to create isolated environments. We want to create virtual machines often. And in hardware emulation, we want to be able to operate unmodified operating systems which were designed and implemented for different hardware architectures. So maybe we want to run an operating system which was designed for a different sort of computer, and we want to run it on our computer without modification. So the entire hardware needs to be simulated, needs to be emulated. One software which is often counted to the group of emulators is Wine, but that's a mistake. Wine is not a Windows emulator. It emulates the Windows API, the interfaces of the Windows operating system. So it's not in first place suited for running a Windows of a different, which was designed for a different architecture on our system. No, it's just designed to run Windows applications inside an operating system which does not have the Windows API implemented. Hardware emulation is very resource consuming. It consumes a lot of resources, and the implementation is very difficult. Because you need to implement everything from a different hardware architecture. Everything needs to be simulated. So in regard of performance and development effort, it's a bad thing. But for some applications, it's the only option you have. But try to remember, emulation is not virtualization. And when we check the list of emulators I prepared here, it's not many popular names we have here. And when we check these names, many of these software solutions are focused on running computer games. So it's also often maybe a niche product. So here we can see we have the hardware, we have the host operating system on top, bare metal, and on top we have the applications running inside running on top of the host operating systems. Running on top of the operating system, and one of these applications is maybe an emulator, and the emulator emulates an entire hardware system, computer system, and so an unmodified guest operating system designed for a different architecture can run, and on top applications inside this emulated system. So the next slide here has a table of some emulators I know. It's not a complete table, and it's not an up-to-date table, but it's just a tiny overview. And so we can see many of these emulators focus old school computer games, designed for for DOS operating systems or old-fashioned Windows operating systems, or it's for the emulation of obsolete end-of-life hardware like old-fashioned Mac, Apple Mac hardware. Maybe the most popular name for some of you maybe is MAME. Yeah, MAME is a very important project for saving old-fashioned arcade games from fading away. Yeah, because hardware to run arcade games is hard to acquire, hard to find, and usually very old and very expensive, and so you can save old arcade games from fading away from history. So another name which is really important here is QEMU. QEMU is an emulator for a personal computer, and it's a base. It's used for many purposes in many virtualization solutions to emulate specific parts of the virtualized systems, but we will talk about this in a few minutes again. Yeah, two interesting emulation projects at least I want to show you in detail, because I'm a bit fan of them. I think some of these projects are really cute. And just to show you what interesting things some people do, here one example, JS-NAS, that's an emulator for an old-fashioned Nintendo video game console, and it's implemented entirely in JavaScript and can entirely runs inside a browser. Inside a web browser. The source code is available, and so you can also just play in your browser. So and it's free software. So I'm a big fan of such things, and it's very interesting to see that such things are even possible. Another example, which is even more impressive, I think. One guy here implemented an entire computer emulator for the browser, also in JavaScript, and so you can run Linux and even Windows instances in your browser by a JavaScript personal computer emulator. If you want to test it, if you want to play around with this, no problem here. The URL is provided, and so you can see you have several operating systems available to choose of. Yeah, we have here lightweight Linux systems, we have Windows 2000, FreeDOS, Fedora Linux, and so on. And so you can just start emulated personal computer here with one of these operating systems, and it works very well. It's very interesting, and I think it's very impressive. Yeah, that's emulation. So we discussed now partitioning and emulation. Now let's talk about real virtualization, I might say, or virtualization which is closer to our daily life maybe. And I'm quite sure every one of you was in touch several times in the past with application virtualization. Application virtualization means we just want to isolate single applications, and isolation means it means two things basically. One thing is we want to be independent from the hardware, physical hardware. So application virtualization can imply we have a different architecture. and we run software for this different architecture in our small virtual machine. That's exactly what we have when we talk about Java. The Java runtime includes the Java virtual machine, and the Java virtual machine is an application between our Java applications and the operating system. And the Java virtual machine executes the Java bytecode, which is created by the Java compiler. So the Java bytecode is independent, architecture independent, and so that's the reason why you can run your Java applications everywhere where the Java virtual machine is available. So it's platform independent, but we lose some performance. The effect is not so strong anymore since we have just-in-time compilers and so. But it's still not so fast compared to native program execution usually. That's one of the two sorts of application virtualization. We are independent from the hardware architecture because we have different bytecode. Another scenario of application virtualization is something like SynApp. SynApp is one example of a software that can be used to isolate applications from the host operating system and the remaining applications, just to make it more secure and just to increase portability. So SynApp is one example here where you can pack Windows applications into single files, executables, and these executables include everything which is required to run the isolated application, the libraries, and so, and you can transport your applications very easily by using a flash memory drive or by downloading it, and you will not modify the operating system where you execute the application, so nothing is deployed or modified there. So it's basically a sandboxing, a sandbox scenario. Here we don't have a different bytecode. So here we stay inside the architecture specification. We just isolate an application. And if we talk about this, it sounds very familiar with a solution you maybe have heard about with something like Docker or so. Docker is one of the examples, popular examples of operating system level virtualization. And here also we create isolated environments. So honestly, the boundaries are not very sharp between these two different concepts, and later we will talk about operating system level virtualization again. But something like SynApp it flows a little bit. Docker, for instance, if we stay with this topic, it can be counted, or is usually counted, to operating system level virtualization, but often people use it like it is application virtualization, because something like Docker is usually used to just isolate single applications. So now let's come to one of the big player concepts, we have two concepts which are more or less state of the art when we talk about virtualization of systems on personal computers and commodity hardware servers. That's full virtualization and para-virtualization. And both of these concepts, they implement, each one implements a component called hypervisor. Again, the hypervisor. You remember in partitioning, we also talked about a component called hypervisor, and I promise to you we will get it again. So, full virtualization is basically what you get if you deploy VMware Workstation or VirtualBox, or if we talk about the kernel-based virtual machine. So in virtualization, full virtualization, sorry, the software solution, it creates virtual machines which are replications, virtual replications of entire computer systems, entire personal computers or so, or entire server systems, and including a BIOS. So it's really like a virtual machine. You can switch on, switch off, and so. These virtual machines have virtual resources like CPU, main memory, block storage, I/O interfaces like network interfaces, and for the implementation, for providing these features, we have one software component which is required, and that's the hypervisor. The hypervisor is in literature called a virtual machine monitor, if we talk about full virtualization, virtual machine monitor, or so-called type 2 hypervisor. So the type 2 hypervisor runs on top of a host operating system, and it runs like an application. Yeah, sometimes in literature people say it runs hosted like an application, and some components, they cannot be used in a virtualized way very well, so they need to be emulated. Emulation means here means some hardware components like network adapters or so. Like network adapters, they cannot be used by multiple operating system instances at the same time very well, so they need to be emulated, and that's again where we talk about things like QEMU or so. Another benefit, if you emulate some hardware resources, you get rid of all driver issues, yeah, because if you emulate maybe a network interface card with a very popular device from the past, so you will never run into driver issues. So for deeper understanding of full virtualization, it makes use to repeat some basics of the computer architecture we usually use every day. Most of us use the Intel architecture, and so the Intel architecture has, as you might remember from when we talked about processes and process management and system calls and so, the Intel architecture has 4 privilege levels implemented. General idea, we want a separation between kernel mode and user mode. So in kernel mode we have the kernel, and in user mode we have the applications. The kernel can access every hardware and every main memory resources, and in user mode the applications can only operate on their virtual memory, can only operate in protected mode. So we have ring 0, you remember maybe, and ring 3, and this ring specification is a bit confusing because we don't really have rings in computer systems. It's just a specification by a register value. Yeah, the running process. If you want to know to which privilege level does it belong to, there's one register which indicates this. Yeah, and here we have one link to an important topic we discussed about. It's protected mode. You remember from slide set 5 maybe. And back in these days when we talked about user mode and kernel mode, we also talked about why the modern operating systems usually only implement support for 2 privilege levels. It was just to keep it portable, and and just because there were a lot of hardware architectures in the past which had support for just 2 privilege levels. But okay, old-fashioned things. You also might remember processes running in user mode if they want to carry out higher privilege tasks like request shared memory segments or access some hardware. So processes need to carry out system calls, and the system calls are catched by the operating system kernel, and the kernel needs to handle these system calls and try to carry out the requests. So that's what we discussed in slide set 7. So let's get back to full virtualization. If we talk about full virtualization and its implementation, so we have learned, we have in ring 0, usually we have the kernel there, the operating system, host operating system, and in ring 3 we have the applications. So the full virtualization concept specifies we have the virtual machine monitor running besides the applications on ring 3. It's a non-privileged application, but it needs to talk to the host operating system, and it needs to provide some features for the guest operating systems, for the virtual machines. And so that's done by an extension for the host operating system kernel by a module, and the guest operating systems, the virtual machines, they are isolated in ring 1. So they are less privileged than the kernel mode, and they are isolated from the remaining host operating system applications. So the virtual machine monitor is a pretty complex software, definitely, because it needs to include a treatment. Yeah? It needs to handle all privileged operations, all system calls from the guest operating systems, and it needs to schedule these system calls usually. Um, the virtual machines have no direct access to the hardware. Everything say demand, everything say request needs to go via the virtual machine monitor. And so maybe you remember, if we have many interactions between processes and the operating system, we are talking about many context switches, yeah, process changes, and requests going to the operating system and back. So here the number of context switches it gets increased. Yeah, so we will definitely waste some resources. So yeah, benefits. Strongest benefit maybe we have very little modifications on guest and host operating systems here. We have quite good performance on modern hardware. Yeah, it's not so bad if we compare the benefits. The overhead we need to accept, and each guest operating system is like a full virtual computer, so it's like a virtual machine. Yeah, it's a virtual machine. So it has its own operating system kernel, independent from each other virtual machines, independent from the host operating system, and so it's a very flexible concept. So you can easily run Linux instances, different Windows instances, and so at the same time on the same hardware. You can try out different kernel revisions, you can try out different operating system revisions, and so it's interesting for development and so. Yeah, but drawbacks, we have the context switching, we will lose some CPU resources definitely, and yeah, that's the main drawback. Yeah, I mentioned before some examples of implementations of the full virtualization concept. Yeah, it's, for instance, VirtualBox you can get for free, and I know it's used by many people to run a Windows or Linux on your laptop or so in our university. So VMware products, which are quite popular among end users here, like VMware Server or Workstation also. Parallels is quite a popular solution in the Mac world, and in the Linux world definitely the most popular full virtualization solution is the kernel-based virtual machine, because it's a part of the Linux kernel already, but it has some differences compared to the architecture explained now. And because the kernel-based virtual machine is state of the art on almost all server systems around now and on many workstations, so it's worth a bit deeper look. So the kernel-based virtual machine, it allows to transform the Linux kernel into a type 2 hypervisor, yeah, and that's done by two modules. You remember Linux kernel modules, they are outsourced of the Linux kernel, run outside the Linux kernel, but with the same privilege levels as the Linux kernel. So they run in kernel mode, and for this reason the Linux kernel is still a monolithic kernel. But we don't care about this now. It's just two modules, the KVM module and a module which is designed for the hardware architecture. So we have an Intel one and an AMD one, but the naming is a bit confusing. Every one of you which has an Intel compatible chip inside its machine, I'm sure uses now the AMD module, because Intel adapted more than a decade ago the AMD virtualization implementation, and the Intel implementation basically died out. So yeah, if these modules are loaded, the kernel itself becomes a hypervisor and can be used to create and not administrate is the wrong term, modify virtual machines. So in KVM, quite interesting, KVM does not offer any virtual hardware, so that's done by the QEMU software, by the QEMU emulator we mentioned before. And so we have a differentiation here. The CPU virtualization is implemented by the CPUs itself, by the Intel or AMD CPUs. The main memory and storage is virtualized by KVM itself, using the Linux kernel, and the I/O is virtualized by QEMU emulator processes. So yeah, full virtualization, that was one of the two, I'm quite sure, most popular virtualization techniques on servers and workstations. The second one is para-virtualization. Para-virtualization is quite different to full virtualization, because here we have no hardware virtualized or emulated in any way. The host operating system is replaced. It's replaced by the hypervisor again. Yeah? The software component which does all the virtualization stuff here, the hypervisor, it's called again. But now it's called a type 1 hypervisor, and yeah, it runs bare metal. It runs on top of the hardware without an additional host operating system. So the hypervisor is basically like a meta operating system, so it will distribute the resources, it will collect requests, and it runs in ring 0. So it truly replaces the host operating system. The guest operating systems again are transferred or are relocated to ring 1, to the less privileged ring 1, and so again they are separated from the applications. Stupid question, where do the drivers come from? Yes, that's always a big thing in operating systems. If you want to implement a new operating system, people will complain all the time, what's about my devices? Can I still use my graphics card? Can I still use my sound chip? Can I still use my network interface card, and so on? And the implementation of so many device drivers for stuff around in industry, that's pretty difficult. So a hypervisor which replaces the operating system need to include all device drivers required. Alternative solution would be the hypervisor need one guest operating system which includes all the device drivers required, and it just uses these device drivers to satisfy the requests of the other operating systems. So we need one special guest operating system in such a case. Okay, so for the most simple concept in para-virtualization, we have the hypervisor which replaces the host operating system, and so one might remember or one might understand. So the guest operating systems now they run in the less privileged ring 1, so they cannot execute any privileged instructions, and so the hypervisor need to implement something called hypercall support. So hypercalls are something like system calls. You remember system calls are operations that allow the software to request operations, higher privileged operations. And so the hypercalls now they are used as replacement functions for the system calls, because the system calls cannot be used here by the guest operating systems. So the hypervisor will order the execution of system calls via the kernel API of the operating system because of the hypercall feature. In effect, the guest operating systems need to be modified. They need to be modified in a way that they can handle the hypercalls. Modification is a difficult thing because if it's open source, it can be done. If it's closed source, the software vendor of the operating system maybe has no interest in allowing this or doing this. That's the reason why para-virtualization in this pure software way was not able, for instance, to support Windows guest virtual machines also. Para-virtualization, nevertheless, is implemented by many solutions. Everything which is called Xen is based on para-virtualization. Xen, the freeware revisions, so the open source versions, and also the versions from Citrix, but also stuff like VMware ESX server, it uses para-virtualization. The drawback of having to modify the guest operating system is not a big problem any longer, because today, well, not just today, since 1.5 decades, it's state of the art that we have hardware, that we have virtualization support in the hardware. But we will talk about this in one slide. Before, I again want to tell you something about Xen, my poster para-virtualization application or para-virtualization solution. If we talk about para-virtualization, the hypervisor need all device drivers inside implemented. If we talk about stuff like VMware ESX, this para-virtualization solution need to be is permitted to run only on specific hardware which is certificated. So you can be sure all device drivers are inside the hypervisor. If that's not the case, something like Xen will run or will demand that you have at least one operating system running, and this operating system, this guest, it is used to deliver the device drivers. And in Xen, the virtual machines are called domains, and one domain is the DOM0. And the DOM0 is the most important virtual machine or domain because it delivers the device drivers for the hypervisor. And if less privileged guest operating systems, so-called DOMUs, domain unprivileged, if they request some resources, if they call system calls or so the device drivers are delivered by the DOM0. That's a bit weird concept, yeah, but it's the best solution if you have such a challenge, yeah, because you cannot re-implement all device drivers, and easiest thing is you run a Linux in as one virtual machine, and you use the device drivers already inside the Linux kernel. So yeah, drawbacks as mentioned before. Guest operating systems need to be modified. With open source systems it's not a problem, but with closed source systems it's challenging. But the performance is good if it's implemented. So present day, I mentioned before, it's not a big trouble anymore. I'm too fast. So again, here we have a small summary. Yeah, sorry. We have the para-virtualization, we have the full virtualization. Para-virtualization needs the guest systems to become modified. In full virtualization, not. We can have everything unmodified. In para-virtualization, we are talking about type 1 hypervisors that run bare metal, that replace the operating system. In full virtualization, the hypervisor runs hosted, like an application in the host operating system. And in para-virtualization, the hypervisor in ring 0 has full hardware access. Yeah, it needs to have it. And in full virtualization, the hypervisor, the virtual machine monitor, it runs in the same level as the applications. And here again we have some standard solutions around, some examples of implementations of these concepts. So, and now we have the reason why it's not a big trouble anymore if we want to run closed source operating systems in virtualized environments at all. So reason is the CPUs around since 1.5 decades, they have hardware assisted virtualization as a feature implemented, and so we can now run unmodified guest operating systems easily. At the very beginning, the solutions from AMD and Intel were incompatible with each other. Interesting enough to say, the AMD implementation won. And so Intel was forced to adapt the AMD implementation. So because no one wanted a split here and having the requirement to have different implementations of the same virtualization software. Hardware assisted virtualization means we have an additional privilege level. We have an additional ring. Depending on the literature you check, it's called ring -1, or it's just called the root mode. So in effect we have an additional privilege level which is used for the hypervisor, and ring 0 is still available for the guest operating systems, and so there is no need to modify anything inside the guest operating systems. They just can deploy it in a non-modified way. The virtual machines, sometimes they are called hardware virtual machines in literature now, but most significant thing again is you don't need to modify them any longer, and so it's not a problem to run maybe a Windows system in a Linux host environment. So we are getting closer to the end. I told you we have two strong concepts around, two main concepts. Honestly, that's not true any longer. That's an outdated information. I think I should say three concepts for running virtual machines, because the operating system level virtualization gained a lot of popularity in the past years. I think we have a question. Oh, okay, yeah, come on. A hand is raised.
Sorry, are you talking about me?
Yeah, okay, it was a mistake. Okay.
Okay.
So, the third concept, which is very popular since a few years, it's the containers. Some operating system families it's called jails, but container is the more popular technical term. In a container solution, we can not run additional operating systems. We can only run multiple isolated environments of the same operating system, or inside the same operating system. So you cannot run different kernel revisions, for instance, or you cannot run here a Windows and a Linux at the same time or so. It's just instances of the same kernel, basically, or the same operating system instance. The applications inside these containers are isolated from each other, so they cannot cross the containers, cannot relocate between the containers. And maybe you might think now, that's not a good thing because it has less features than full virtualization or para-virtualization. But the strong benefit here is the low overhead. You will not waste many resources if you do this. But the drawback is everything uses the same kernel and it's lesser flexibility. If you want to execute isolated applications and many of them on the same hardware, it's maybe the perfect thing if you can live with the drawbacks. And maybe if you ever wondered why virtual root servers in the internet are so inexpensive, that's because you can run many container instances on one physical hardware without trouble and can sell this in the internet or run it for yourself. Security is quite good, performance loss is quite little, And that's also not a very young concept. So if we check this list here, the change root feature of Unix systems, which is quite old now, it goes into this direction. And yeah, Docker is definitely most popular implementation here now for containers, but also the BSD jails, or in Linux the virtual VS server implementation and so. So that's quite popular if you want to rent virtualized root servers. So that's it about truly virtual machines or isolated applications, but we still have implementations of different virtualization concepts around, which are sometimes relevant for data centers, but sometimes also relevant if we are talking about complex networks, or if we talk about network services. So one of these additional concepts here, which is relevant for data centers mainly, is storage virtualization. Storage virtualization means we have network attached storage or storage area networks, and virtual block volumes are offered as drives over a network, over a computer network. And these virtual volumes, they behave like a physical block volumes, so you can partition them, you can create different file systems on top, and in a physical way the data is distributed in the storage area network across many physical drives, and so it's basically a transparent RAID, and also it's distributed so it's more failure safe and it performs better. That's a much better concept than having here the traditional way where you just assign physical block drives over a network to single machines, and so they need to take care about stuff like backups and so by themselves. Stupid question, why is not everybody doing this? Reason is it's super expensive. Such storage area networks are quite expensive, but for data centers it's state of the art. It's a different concept compared to these network attached storage drives you can buy for a few $100, because here usually you don't have block level exports. Last but not least, we also have virtualization in computer networks. I'm not sure if you have learned this in computer networks class up to now, but so we can have just 2 or 3 slides about this now. Network virtualization means you can have independent logical, which means virtual networks on top of physical networks. So these virtual networks, they separate physical networks into logical subnets or overlay networks. You can call it as you like here. Switches, which need to the switches you operate need to be able to handle this. And so the switches will take care that the virtual networks are separated from each other, and packets are not forwarded into the wrong into the wrong virtual local area network. Yeah, it's a quite good thing if you want to consolidate devices, resources, that belong together because they have, because of the ownership or because of security level or so. This can be done by two different sorts. First, we have the old-fashioned one, the static one, which means manageable switches can be configured in a way that specific ports are assigned to specific virtual local area networks. It's a permanent assignment, and so it cannot be automated quite well, and so we have a separation of the logical networks. The smarter alternative, the smarter way to work with this technology is the dynamic one, which means we use the so-called virtual local area network tag, and that's a part of every network layer package, which is not from an end-of-life device. Yeah, it's state of the art since I don't know, maybe 2 decades or 2.5. And so by specifying the information in this virtual local area network tags, the networks can be separated from each other. And this can be done in an automated way. So you might remember from computer networks course the structure of an Ethernet frame on data link layer. And so here in the center of this image here, which is not very smart because here we have maybe many bytes payload, and here it looks like it's in the center, but it's not truly in the center in real life. So here we have this virtual local area network tag, 4 bytes, and a part of these 4 bytes, so here we can see it, is 12 bits. It's the ID, and here we have a priority information, and so we can separate the virtual networks according to their IDs, and we can assign them different priority levels, which is pretty useful if you mix maybe important services and less important services. And technology explaining without example, I think it's always a bad thing. And so here we have some examples where virtual local area networks are used heavily. One example is Telecom Entertain. I'm not sure if someone of you has this service offering. So here we have broadband internet connection, and we have telephone as service, and we have television as service. It's a so-called triple play offering. So two virtual local area network IDs are used here to separate services from each other, because the television service, it is regarded as something more significant than just surfing around in the internet or playing computer games. And so we have two different virtual networks here with different IDs, and so the television network is considered as more important. Next example is Eucalyptus. Eucalyptus is an infrastructure as a service cloud private cloud implementation. It's a free software you can use to build up your own infrastructure as a service private cloud with one or many Linux servers around. So this software uses virtual networks because the virtual machines, the instances, they are always assigned to so-called security groups, and inside these security groups you have firewall configuration. So you specify which ports are open, and the security groups are separated from each other by virtual local area networks, because that's also a separation of user groups. Yeah, and last but not least, if you have a home office with different people, maybe with children or so, or if you're working in a data center, um, there it also makes sense to separate the applications from each other and the people from each other for security reasons, or just to prevent issues with your production network, because people play around and so download every stupid thing, and so you just want to get away from this. So, last but not least, a small overview about benefits and drawbacks, or some motivations, some reasons for virtualization, and also some limitations. That's a better terming. So, if you want to use virtualization, one benefit is you can consolidate your server systems. Yeah, you can utilize your hardware in a better way, because you merge systems on lesser hardware, and you maybe save some money because of less hardware costs and maintenance and electric energy consumption and waste heat and so. Administration can be simplified if you know what you are doing and if you have the right tools around. If you don't have, maybe it gets worse. Yeah, but virtualization has the power to allow you relocation, duplication, backup of virtual machines, maybe during runtime without a hassle. And also you can have the snapshot feature. So if you want to play around with something, or if you want to deploy updates, you can try with snapshots if you run into trouble. Next, the deployment of infrastructures and servers is simplified, can also be done in an automated way in moments, and security level, it may get increased. Yeah, if you know how to protect your machines from each other, it's basically the same as working with physical machines. So maybe you can even increase security a little bit. One strong argument is also, if a virtual machine breaks, it has nothing to do with the remaining ones, or the host operating system, if you have one, is not affected. Last but not least, legacy systems. So in industry and so, it's state of the art that software often runs and runs and runs, and systems get older and older, and people usually try to avoid needing to migrate. Migrations are always maybe it works, maybe not, and people tend to say, I want to keep my systems as long as it gets. So if the hardware has reached end of life and need to be replaced, or if it's just broken, maybe running a stable system, which is quite good, maybe running it into an isolated virtual machine environment is a good idea. So it can run for years and decades again. And last but not least, some drawbacks and limitations. First, the performance loss. Yeah, you will definitely lose resources if you play around with virtualization. It's not so bad today, but We cannot talk it away. It exists. Um, you cannot emulate or reach every hardware from virtualization environments. Some stuff is difficult to implement or not even possible. GPUs are sometimes challenging. Hardware dongles are a big problem. And yeah, if a host that runs virtual machines, if it fails, not just a single machine is gone, maybe many machines are down. But this can be fixed if you know what you are doing, and maybe if you have multiple instances and you have load balancing and so. Yeah, and last but not least, virtualization is complex. Yeah, it's sometimes hard to understand and hard to get around with it. So people need additional know-how, and people tend to say, "Oh, I don't like this. Yeah, I don't want to become familiar with this." And so that's it. Yeah, that's our short introduction into virtualization. Um, do we have some questions before I have some good news for you?
I have one question.
Yes.
I remember during one of your first lecture, you said about the thin kernel,
Yes.
and we used the thin kernel for the type 2 hypervisor, right?
Um, mm, no, you don't need.
This,
No, that's mixing things up which do not belong together. Um, Type 2 hypervisor is the full virtualization that has nothing to do with thin kernels.
okay, because I remember reading somewhere. Must be
Okay.
mistaken.
Show me later, or show me next time.
Okay, yeah.
Do we have another question before I have some good news for you? Oh, we don't have. So, some good news. Um, During the weekend, I created your exam, and I decided covering the first 9 slide sets is enough. So I decided I don't will have any virtualization related questions in the exam. So slide set 10 is not exam relevant. I hope you are not too much dissatisfied or angry about this. Yeah, next week we have one session left, and it will be a pure Q&A session, questions and answers. So I will be your mindless robot trying to answer you questions, and you might ask stuff like, hey, please explain this or that again, or please tell us again how does this work. So I will just try to help you as long as you are happy to go away. So please use the time until next week to prepare yourself for the exam, and so you have some understanding about the topics, and you understand where you have questions, what questions you have, and so you can ask me whatever you want next week. Some more questions? Oh, ooh, it's not loud enough. Please increase the volume a bit if there's a question.
Can you hear me now?
Wow, you are so hard to understand. Okay, again?
Hello?
Yeah, hello.
So the problem I have is Okay, so you said earlier in the slide that the virtual box can support the hardware virtualization.
Yeah. VirtualBox also supports yeah, definitely the hardware assisted virtualization of the modern CPUs. Yeah.
But that I do not understand because I thought the virtual box is just an application running on the host system.
It's
Because
not just the application you see or you interact with. It's also always an extension to the host operating system kernel. And so the main feature, the main functionality is done by the kernel extension, which is deployed if you install VirtualBox. In Linux you can see this very well because depending on the Linux distribution you run, this Linux kernel needs to be compiled on the fly and you can monitor this, and so it needs to be recompiled every time when you update your Linux kernel or when you update VirtualBox. So it's both. It's the component on application level, and it's the component on host operating system level.
I understand.
It's okay?
It's okay.
Okay. Any more questions?
I have a question.
Yeah, very well.
Can we use like multiple type of virtualization at the same time?
You can do nested virtualizations, which means you can run in a virtual machine another virtualization technique. That's called nested virtualization. In many virtualization solutions like VirtualBox or VMware or so, you can you need to enable this. But yeah, it's possible, and for professional solutions like VMware ESX or so, that's not a trouble. Yeah, that's possible. Yeah, sure. And mixing maybe containers inside virtual machines of full virtualization or para-virtualization is no problem at all. But even nesting full virtualization is possible. Okay, so thank you for attending our final session here with slides, and please prepare yourself for the exam, and please if you have questions attend the exercise sessions and attend next week's Q&A session. So, and thank you again for attending. Bye bye. Can we yeah, you can have the same material as every semester. So bye bye.